Hello, AP Chemistry students, and welcome to AP Chemistry video. Today, I'm going to share with you some calorimetry examples. We are on page 14, and we're going to go through about page 16. Okay, so depending on which class you were in, you may have started at a different place, so you may fast forward to where it's applicable. But for most students, we started right here at the top of page 14. So in class, we will be conducting what's called constant pressure calorimetry experiments. This is a type of calorimetry normally used to determine heat transfers in reactions taking place in aqueous solutions. So things like acid-base reactions, double replacement, maybe some single replacement, whatever, if reaction happens in an aqueous media, it's fair game. We also could set up experiments to determine the heat capacity or specific heat of certain substances. So we'll talk about that example too. All right, as you may have already seen if you've had lab, the basic setup is two, not just one. Actually, it doesn't really matter, but two works better than one. Two nested styrofoam cups with a cover through which a thermometer can be inserted. A reaction takes place, and please notice that the pressure, because the lid has an opening, is constant, meaning the pressure inside the cup and outside the cup will be equal or equal to atmospheric pressure. So that's where the term constant pressure calorimetry comes from. We will talk about constant volume calorimetry a little later. All right, the most important part. It's in bold. I'm putting 18 stars next to it. So the basic idea of calorimetry is pretty simple. The heat given off by some kind of process will be absorbed by the liquid in the cup. We'll call that the surrounding liquid. The surrounding liquid in the cup and the calorimeter itself. So the nice little styrofoam cup we're using might absorb some of the heat. Okay, so I'll say that one more time. The heat given off by a certain process, some kind of reaction, whatever, will be absorbed by the surrounding liquid in the cup and the calorimeter. Okay, and if it's an endothermic process, it'd be exactly the opposite. The heat absorbed by a certain process will be released by the surrounding liquid and calorimeter. So we will typically say that the heat absorbed or lost by the calorimeter is negligible though. So let's see how this all comes together. So I'm going to take what was said here and put it in symbols. So the heat given off, our symbol for heat is Q. Oh yes, look, there's the bell. Please excuse that. So the heat given off, we'll call that Q of reaction. So make sure and label your Qs. That's extremely important. It's going to equal the heat gained, okay, by the water. And the water, it might not be pure water, but it's the surrounding liquid and the cup itself, which is the calorimeter, okay? So the heat lost will equal the heat gained, but notice I'm going to put this negative right here. Now, all that negative means is that these two quantities, the heat from the reaction and the heat absorbed by the water in the calorimeter, they will be opposite signs. Okay, so you guys are going to see how that works in a minute. And I can even take this and separate it out a little further. So if you guys are looking for the heat of reaction, well, how do you figure out the heat absorbed by the water? Okay, well, that would be the mass of the water times the specific heat of the water. That's an H2O times the change in temp of the water. Okay, and likewise with the heat of the calorimeter, you can figure that out. And the heat of the calorimeter would be the specific heat of the calorimeter times the change in temp. Okay, but we are going to say that we're using like super amazing insulated, like high quality Starbucks calorimeters. So as a result, for most experiments, we will assume that the heat gained by the calorimeter itself is negligible. Okay, so we will usually say that this part of the equation is zero. Okay, so this is the reaction, or the formula, I should say, that we will work with for most calorimetry experiments. Okay, so let's go ahead and give it a go. How does that sound? So we have an example. So basically, you want to make sure that you can envision what's going on here. So you have a 44-gram sample of an unknown metal at smoking hot 99 degrees. It was placed in a constant pressure calorimeter containing 80 grams of water. So you guys have this super hot metal, and then you're putting it in the cup calorimeter that has like room temperature water. All right, not surprisingly, the final temperature of the system, okay, the water with the hot metal, goes up to 28.4 degrees. So it says calculate the specific heat of the metal. So I would love for you guys to go ahead and just set this up. But the one thing I want you to do first is make sure you have a clear picture of what's going on with your Qs. So for instance, in this problem, you have the heat lost by the hot metal, okay? whatever heat is lost by the hot metal is going to be gained by the liquid in the cup. Yes? So we'll call that Q of water. And again, we'll say the heat absorbed by the calorimeter, we won't even consider that. Okay, and just remember the heat lost by the metal, okay, is going to be gained by the water. It's the same Q value, but opposite sign. Okay, and you can go ahead and you can flesh this out a little bit more with your Q equals MC change in T. So the heat lost by the metal, you got the mass of the metal, the specific heat of the metal, change in temp of the metal. Yes? Okay. So that's all the variables that go with the metal. And then equals the heat gained by the water. So now we're talking about water. So that's mass of the water, specific heat of the water, and change in temp of the water. Yes, you see? So you guys can go ahead and plug in those numbers, and our goal is that we want to solve for the specific heat. So I challenge you to go ahead and work through this problem and then resume the video and check your answer. So, okay, so how did you do? Now, one thing I want to point out is notice that when I worked through this, I actually did it step by step. So the heat loss, so first of all, with calorimetry, you always look at what's going on with the surrounding liquid. And then from that, you can figure out what's going on with the thing you're interested in. In this case, what's going on with the metal. So I looked at the mass of the water, specific heat of the water, change in temp of the water. 1,500 joules of energy was gained by the water. Okay, so notice that that's a positive quantity. It was gained, it was absorbed. Okay, and here's my favorite question. So whatever amount of heat is gained by the water was lost by the metal. So what's Q lost by the metal? Same number, opposite sign. Because of course the metal released that energy. Yes? And then you can take that number and do your Q equals MC change in T for the metal. So now you got the heat lost by the metal equals the mass of the metal, specific heat of the metal, change in temp of the metal. Remember the metal started off really hot and then went down to 28.4, that temperature that was in the middle. All right, so hopefully you guys got an answer of about 0.48. Make sure you have units, joules per gram per degree Celsius. And hopefully you guys see how those units happened, okay? So this is one experiment that we're not gonna set up, okay? But hopefully you get the idea how it works, okay? And there's some out questions that are just like this. All right, so we're gonna continue on. Now these next two examples are way, way, way more what we're gonna do in chemistry like all the time. So we are gonna look at the heat released in chemical reactions. So in this first example, it says, okay, so you got 100 mils of 0.5 molar HCl mixed with 100 mils of 0.5 molar NaOH in a constant pressure calorimeter, basically a styrofoam cup. Okay, and we don't care about the heat capacity of the cup. Okay, the initial temperature of the two initial solutions was the same, but then when they're mixed, it went up to 25.86. Here is the balance equation. So first question, just from the data provided, is the neutralization reaction X or endo? Okay, you can tell. So the basic idea is that the surrounding liquid, what my thermometer was sitting in, went from 22 degrees to 25.86 degrees. So the temperature went up. So that means that the surrounding liquid was absorbing energy. Well, where the heck was it getting that energy from? Okay, so it was getting an energy from the process or the system, which was this reaction. So that means the reaction was exothermic. Okay, so could you explain why, right? So again, go ahead, just put that in your own words, okay? Okay, so now to the fun part. So letter B, so now we're actually gonna do calculations to support that. So calculate the amount of heat absorbed by the water, absorbed by the liquid, okay? So the heat gained by the liquid, so we're gonna use Q equals MC change in T. Notice our mass of liquid. So we took 100 mils of the HCl and 100 mils of the NaOH. So together, how much liquid is in the cup? Okay, there's 200 milliliters, correct? Now, being that these are both aqueous solutions, they're pretty much going to behave just like water. So the density of water is 1 gram per milliliter. So 200 milliliters of total volume is going to be about 200 grams total liquid. Okay, so we got 200 grams. We got the specific heat, again, since it's an aqueous solution, it's going to be the same as water. And then here's our temperature change, okay? So the heat gained by the surrounding liquid in the cup was 2810 joules, all right? And then, like I said, my favorite question, what is the amount of heat then lost by the neutralization reaction? Okay, so the surrounding liquid absorbed energy, so the reaction lost energy. Okay, so same number, but opposite sign. And please notice how I'm labeling all my Q's so I can follow along what heat quantity I'm talking about. All right, So good so far. All right, so now probably the second most important thing I'm going to say. So we've been talking all about Q, right? And Q is the amount of heat released or absorbed by your random amounts in your experiment. Okay. What is delta H? Okay, so now I'm going to ask you to solve for delta H this reaction. That's called the change in enthalpy. And it's basically the exact same thing. It's the same thing as Q, the heat gained or lost, but it's per mole of limiting reactant. Or so more, I could say it another way, it's per the balanced equation. Okay, so we're going to go back to the same example. It says reconsider example 4 above for that neutralization reaction. Okay, now it says calculate delta H for this balanced neutralization reaction. So this is what we're looking for. So number one, we got to check to see if there's a limiting reactant. Now in this experiment, well, we had equal molar and equal volumes of NaOH and HCl. Okay, so there's no LR. Okay, but you could still justify that, okay, by doing the calculations. Okay, so whether you're talking about the HCl or the NaOH, you pick. Neither one's a limiting reactant, or either one's a limiting reactant. So you got your molarity times your volume, and that's how many moles of NaOH or how many moles of HCl you had. Okay, so to calculate delta H, it's the same thing as Q, but it's per mole of limiting reactant. So I just take that Q value, total amount of heat released, divided by total moles of the limiting reactant. So in this case, you just pick one. Okay, divide that through. That's going to be the heat per mole. Okay, and then I'm just going to go ahead and convert that to kJs because that's a lot more reasonable of a number. And that's usually what happens. Because when we do an experiment, we usually do it on a small scale. So we don't have anything close to a mole. We're like 0.05 moles, right? So then when I scale it up per mole, okay, the number is going to get astronomically larger. Okay, so for this balanced chemical equation for 1 mole NaOH and 1 mole HCl, we're going to release negative 56.2 kJs. Okay, so take-home message is Q is the amount of heat released or absorbed for your experiment, whatever amount you used, and delta H is the amount of heat released per the balanced equation, the heat released per mole of limiting reactant. Because if the limiting reactant is going to limit how much product you can make, that same limiting reactant is going to limit how much heat you can make. Okay, what do you think? Stuff is like totally fun. All right, so boy, now it's your turn. So example 6, got another chemical reaction. This time we're making a precipitate. So what I want you guys to do is read through it, okay? And I want you guys to go ahead and set up the calorimetry calculation. I will tell you the final answer comes out to negative 26 kJs per mole of barium sulfate, okay? So I want you guys to work through that. Really do, okay? So do that now, okay? But promise that after you've worked it through, the final answer, you guys have the work here. You can kind of meander your way through, okay? I think it's the same question as before. In this case, trying to remember if there was a limiting reactant. You had 1 molar barium nitrate, 1 liter. So you had same molarity, same volume. So again, there was no limiting reactant. But when you put these two solutions together, that was 1,000 milliliters and 1,000 milliliters. So that was 2,000 milliliters total liquid in the cup. So it was 2,000 grams, right? All right. And because you had 1 molar solutions, 1 liter, you had 1 mole. So that made your delta H calculation pretty easy. Okay. All right. Fun times. Last but not least, far from least, constant volume calorimetry. Honestly, we're not going to talk too much about this, although this is like my total favorite because it goes by the title bomb calorimeter. This is how they figure out the calories for food. So if you take a look, the basic premise is that you take whatever food item you have, and you put it in this little tiny compartment, like let's say a Cheeto, if you will, and then you inject pure oxygen at high pressure. Okay, so this baby's going to burn really well. And then you spark it, the combustion reaction occurs, and from there, it's the exact same as everything else we're doing. The heat lost by this combustion gets absorbed by the surrounding water, and because it's a metal container, it's definitely going to absorb some of the heat. So the heat lost by the combustion reaction is going to be absorbed by the surrounding water and the calorimeter itself. So you do the same old calorimetry calculations that you usually do. Okay, so again, that's typically used in foods. These bomb calorimeters cost like $10,000 or so, but they're pretty sweet. Okay. One little detail about these bomb calorimeters is because it's a constant volume. We call it constant volume calorimetry because the pressure does change. Okay, so the calculations are a little tricky, but we're not going to worry about them too much. So, well, boy, I hope that helps you. From now on, the OWL assignment should be super easy, and you should have a lot of success doing all the application questions that we're going to ask you to do. Thanks so much for listening. Be sure to ask your teacher if you have any